Welcome. Today we are going to be understanding about oceanic circulation. Basically, we are going to be studying how water and the temperature and also the salinity of the oceans are regulated by basic mediums like the foremost among them being ocean currents. Okay, so let's start. The Earth's circulatory system, the mechanics, pathways, and impacts of global ocean currents. How ocean currents form, how they move, and how do they impact our basic climate all over the world. Okay. Oceanic circulation does what? Okay. Oceanic circulation, Oceanic circulation transports heat from one latitude belt to another. Suppose if this is 0 degrees equator, okay, and here we have 90 degrees, right, north. So it will circulate heat to and from one latitude to another, maintaining the habitability of our planet. Ocean currents make sure that no place on the earth is too cold and no place is too hot. So basically it tries to regulate the temperature so that all regions of the earth remain fairly habitable. This is the blueprint of the global heat engine. This is how heat is regulated all over the globe. Okay. Rivers within the ocean. Okay, you know that probably know that rivers are a stream of water flowing in some direction, right? So within the oceans also there are rivers. Basically these rivers represent one ocean currents, a stream of water that flows in some direction based on some characteristics. What are those characteristics? Now let us first look at the definition. Okay, ocean currents, basically the rivers within the oceans. Ocean currents, they represent a regular volume of water. They are a regular volume of water which is moving. It is moving body of water, moving in a definite path and direction. So basically this definition, regular volume of water moving in a definite path and direction, is used to represent rivers. But since this body of water moves within the ocean, that's why these are called as ocean currents. Now let us look at the second point here, the dual engine. What is the dual engine here? The movement is governed by two distinct forces. There are two distinct forces responsible for the movement of this ocean water, okay, or ocean currents. The first one, the primary forces. What is the primary force? Primary forces are those that initiate the movement of water. In order for the water to move from one place to another, there has to be some primary forces involved which will cause the origin or initiation of this ocean currents. Second is the secondary forces. Obviously they influence the currents to secondary forces will influence the currents to flow along specific vertical and horizontal pathways, whether the ocean currents are moving up, down, right, left, okay, which direction would they take, right, or what will be their speed and force, that will be dependent on the secondary forces. So two basic forces would govern the movement. The primary drivers of initiation, right? So when we say primary forces, these are the primary forces. We have four primary forces responsible for initiation of ocean currents. The first one is solar energy. Okay, solar energy coming from the sun, okay, basically is known as what? Insolation, right? And insolation is responsible for life being possible on our earth. If we did not have energy coming from the sun to our earth, then life here would not be possible because it will be too cold, right? So we need that heat from the sun, okay. So but what does it do? Solar energy, it causes the water to heat up, right, and physically expand. We know that heat causes materials to expand, right? Expansion means what? the molecules in the water will try to move outwards, that is expansion, right? So heat always causes expansion, and whenever there is cold, then it will cause it to contract. So solar energy from the sun, that is the heat from the sun, which is also known as insolation, causes water to physically expand. The second is force, primary force is wind. Okay, wind, it blows on the surface of the ocean, right? It pushes water via friction. Can you see this arrows? Wind is forcing the water to move in some direction based on the direction of the wind. In whichever direction the wind is flowing, it will cause the water to move in that direction through friction. The third is gravity. At the same time, the force of gravity is also working on this water or on the ocean currents, and it is pulling them towards the center of the earth, right? It pulls the water down the pile. Whatever is the pile is there, it will pull the water down. Pile created by expansion, it creates a gradient variation. There will be a gradient variation. Some water will bulge up. Okay, wherever the sun solar energy is more, the water will bulge up, and as the solar energy gets decreased, the water reaches the surface level, right? How does this happen? This is due to the pull of gravity. The gravity is constantly pulling, even the bulging water, it is pulling downwards. Therefore, that creates a gradient variation. What is gradient? If we have a flat plane, there is no gradient. Gradient is when there is some high point and there is some low point. Then a gradient is created. So this gradient is created by gravity. The fourth is primary force is Coriolis force. It intervenes to bend the path of the moving water. Okay, the water is moving in this direction. Suppose water is moving towards the right, but it will come in contact with the Coriolis force and it will change its path, maybe towards maybe upwards, maybe downwards, based on which hemisphere that water body is in. And why would it bend its path? Because of the Coriolis force. What is the Coriolis force? Coriolis force is the force that is generated by the rotation of the earth on its axis. Okay, due to the earth's rotation, this Coriolis force is generated, and it changes the path of the ocean currents. Now let's look at this. We have studied that solar energy causes water to physically expand, right? So we know, remember this, that the equatorial region is the hottest part of the earth, is it not? Because we know that our earth is not exactly a circle, right? In the equatorial area, it is bulging out like this, and it is tapered along the poles, isn't it? Right? If it is bulging along the equator, right, and it receives the solar energy, okay, reaches the solar energy reaches the equator first. Okay, that is why places in the equatorial region are the hottest places on earth. Since these are the hottest places receiving maximum amount of solar energy, the water in this region physically expands because of the high amount of solar energy received. Can you see? Because of this expansion, water level is higher here. It is 8 centimeter higher in this region. That is known as the equatorial bulge. Okay, there is a bulging due to physical expansion of water. Heating by solar energy causes water to physically expand. Near the equator, this thermal expansion raises the ocean level. This dotted line represents the surface level of the ocean, right, in the middle latitudes. Okay, it represents the surface level of the oceans, and the water physically rises up this level. Raises the ocean level approximately 8 centimeters higher than in the middle latitudes. Okay, what are the middle latitudes? When we say around 40 to 50 degrees north or south, right? Compared to the middle latitudes in the equatorial region, this part will become 8 centimeter higher than the middle latitudes. This 8 centimeter differential, there is a difference. Here it is 8 centimeter, here it is 0. Isn't it 0 here? Because it is at the level, surface level of water. This 8 centimeter differential, it creates a microscopic but continuous gradient. Can you see this gradient? This is the gradient. Okay, gradient is always created where there is some high point and low point. This is a high point, this is a low point, so there is a continuous gradient flowing here. Gravity pulls the water down this slope. Why this water is coming down towards the mid latitudes? Because gravity is pulling the water continuously. Okay, pulls the water down this slope, initiating the outward flow. So water will flow away from the equator. Okay. Okay, how does the Coriolis causes deflection? We have learned that Coriolis force causes changes in the path of the ocean currents. How will Coriolis force cause this deflection? The Coriolis deflection and the birth of gyres. This is the word. Okay, it is pronounced as gyres, like fire. Gyre. So gyres. The Coriolis force intervenes on the gradient flow. Whatever flow that we have experienced from the equator towards the poles, okay, the water moves. Why does the water move from equator to the poles? Because of that gradient from the equatorial bulge to the mid latitudes. That's why ocean currents always flow from the equator to the poles. Also from the poles, but from the equator they move towards the poles in both directions. Okay, gradient flow preventing water from moving in a straight line. So water will not move in a straight line because of the Coriolis force. Okay, why? This was the intended path. It was a straight line towards the southern hemisphere. Also the intended path is a straight line, but water does not move in a straight line. Why? Because of the presence of the Coriolis force. So but the Coriolis force acts in two different directions in the northern and the southern hemispheres. In the northern hemisphere, water is deflected to the right. In the southern hemisphere, water is deflected to the left. Okay, this is the northern hemisphere. Isn't this the northern hemisphere? This is the northern hemisphere. Hemisphere that is located above the equator is the northern hemisphere. In this case, what happens? This was the intended path, a straight line, isn't it? But it was deflected to the right. This is the right. Okay, so it was deflected to the right. Okay, and we got this. There was continuous deflection towards the right, and therefore we got the formation of a gyre. That means it gets a circular form, isn't it? Then again, what happens in the southern hemisphere is completely opposite to what happens in the northern hemisphere. This is the southern hemisphere. Okay, in this case, consider that you are facing the south pole. Okay, you are facing the south pole, your head is towards the south pole. Your head is towards the south pole. Okay, you're facing the south pole. The intended path of the ocean current was a straight line, right? But it will not go in the straight line because of the Coriolis force. Okay, what will happen? It will deflect it to the left. Okay, if I'm facing the south pole, right, and my left is this way, right, so it is getting deflected to the left. Continuous deflection towards the left will create another gyre here like this, and here the gyre is like this. Okay, circular movement of water is called as gyre here. Okay, now these large rotating accumulations of water and the flow around them are called gyres. This is a definition. Okay, large rotating accumulations of water and the flow, whatever water flow is around them, these are called as gyres. They produce what? Producing massive circular currents in all the ocean basins. They will create this kind of circular currents in the ocean basins. Without the presence of the Coriolis force, these currents would have gone in a straight direction, but they would not because of the presence of the Coriolis force, which deflects their direction towards the right in the northern hemisphere and towards the left in the southern hemisphere. The depth divide. Okay, there are again ocean currents again are of two types based on where along the ocean they are located. Okay, they might be located in the surface, on the surface, or deep within. Okay, if those ocean currents are just flowing along the surface, okay, then what happens? Volume of water that is carried by the surface currents is very low, 10% of the total ocean water is carried by surface currents. Depth is how much? The upper 400 meters. 400, the top 400 meters would be included within surface currents. What are the drivers here? Dictated primarily by primary forces, wind, solar expansion and Coriolis force. We have already studied this. Deep water currents, on the other hand, there might be some deep water currents where they go much deeper in the ocean. They will include 90% of the total ocean water in their flow. Below 400 meters, right, there is a 400 meter boundary, deep ocean basins. What are drivers? They are dictated by secondary forces, specifically variations in density and gravity. Because of variations in density, like we know that water that is located much deeper are more dense compared to the surface water, and gravity is also works differently from between the surface and the deep water. So these two drivers are majorly at work in case of the deep water currents. Density and vertical mobility. Ocean currents do not just move horizontally, they also move vertically like this. Okay, how does that happen? The deep water circulation is driven by differences in three things. Water density. Water density actually is not three things, it's one thing only, water density, but water density again depends on two things dictated by temperature and salinity. Remember that high temperature, okay, and low salinity would high temperature and low salinity would mean less density, and low temperature or cold water and high salinity would mean greater water density. The sink or the poles here. So their water is cold with high salinity, therefore water is denser in the deeper parts, therefore it is denser. Deep water sink into the deep ocean basins at high latitudes where temperatures, high latitudes around beyond maybe 70 degrees, right, north south. So in that case the deep water is very cold and it is highly saline, where temperatures will go down and salinity will go up, therefore water is more denser. The flow is how does the flow occur? The cold water slowly moves towards the equator and along the basin floor. So it will slowly move towards the equator. From the high latitude or the poles, the cold water would move towards the equator. Then the rise, water starts rising. Where does it happen? It happens at the rising happens at the equator. The warm water or low salinity is lighter. We have studied this. High temperature, low salinity water is lighter. It is lighter, it rise therefore when it reaches the equator, right, salinity becomes low, water becomes warmer because solar energy is higher at the equator, right. So it rises towards the surface, water then starts rising. This rising of water is known by the term of upwelling, okay, and it tries to travel outward to replace the sinking cold water. It goes up, okay, then it travels horizontally. Why does it travel like this? To replace the cold water that had gone into the deep ocean basins. It had sunk in the deep ocean basins. It rises and then moves to replace that cold dense water. This is how vertical mobility through density differences occurs. Okay, measuring the drift. There is something called as a drift. Ocean currents are referred to by their drift. What does this word mean? It is a measurement of speed expressed in knots. Okay, speed of the ocean currents. Strength of a current correlates directly to its speed. Strength, if the speed is more, its strength is more. Speed is less, strength is less. So direct correlation. Velocity drops precipitously with depth. Remember that velocity is higher at the surface for the surface currents compared to the deep ocean currents, okay. So currents are strongest at the surface, always remember, and their speed will decay. Their speed will reduce, they decay rapidly as they descend into the deep basins. So surface drift, can you see? 5 plus knots, this is the speed. Deep drift, less than 0.5 knots. Speed is less, strength is less, the deeper it gets, okay. Thermal transport classification. Okay, how do we classify cold currents and warm currents? Remember that the primary function of the cold currents is to bring the cold water to the warm water areas. Cold water from the poles brought to the warm water areas, okay, in the middle and the low latitudes. Primary function of warm currents is to bring warm water into the cold water areas. Warm currents from the equator and middle latitudes to the poles. In the low and middle latitudes, what is the tendency of the cold currents? They are basically found on the west coast of continents in both hemispheres. Warm currents are found on the east coast of the continents in both hemispheres. High latitude tendency, they are along the higher latitude like 70, 80, 90 degrees. They are found on the eastern coast in the northern hemisphere. Warm currents are found on the western coast of the northern hemisphere. Okay, southern hemisphere is mostly the currents are a little bit different. We'll look at the map. Synthesis. The global heat engine oceanic circulation pattern directly mirrors the Earth's atmospheric circulation pattern. You know na, that there are some circulation patterns happening on the Earth called as cyclones, anticyclones. Oceanic currents also mirror that atmospheric circulation. In the middle latitudes, air circulation is mainly, in the middle latitudes, the air circulation is basically, it is anticyclonic. Okay, since it is the ocean circulation is anticyclonic, okay, and the ocean currents will also follow this pattern. In the higher latitudes, the wind flow is mostly cyclonic, so ocean will also follow this pattern. Monsoonal regions, middle latitudes basically, monsoonal winds actively override and they dictate the current movements. We will also look at how monsoon winds change the direction of ocean currents. Now look at this, polar cooling zones. The blue ones represent cold water, colder, denser and high salinity water. Polar cooling zones, deep blue arcs returning the chilled dense water from the high latitudes. From the high latitudes, this cold, dense and chilled water are moving towards the warm areas. Equatorial heat sinks. In the equatorial region, this warm and light and low salinity water will get transported upwards and downwards along towards both the poles. Dense red bands capturing intense solar radiation along the equator, right? And the third, you have to remember the global mixer. There is one current which is not broken. It is called unbroken. It is called as the name of this current is a west wind drift. Okay, this current is known as the west wind drift. This is the only current that it circles basically the Antarctica, continent of Antarctica. Okay, and it is an unbroken current. All of the currents are very short lived, right? And they break at some point, but the west wind drift is a continuous current. The core thermodynamic rules. What happens is that the warm currents, rule 1, heat distribution. From the equator, the warm currents are originated, right? Warm currents read, they originate between the tropics. Between the tropics, that means at the equator. Tropics are here and here, northern and southern, 23.5 degrees north, 23.5 degrees south. Tropics. Between the tropics, the warm currents are originated. They move away from the equator, carrying the stored solar thermal energy poleward towards either of the poles, North Pole, South Pole. Rule 2, the thermal return. Again, cold currents return from the pole to the equator. Cold currents, blue, they originate in the high latitude, beyond 70. They move towards the equator, right, replacing the displaced warm water. Warm water has already moved towards the poles, so there is a gap there. So cold water will move equatorwards to replace the warm water. It will act as a planetary cooling mechanism. For example, in case of the Atlantic Ocean, this is the Atlantic Ocean. This is the North Atlantic Drift, which is a warm current, okay, originates somewhere along the equator, then moves towards the poles to transport warm water towards extremely cold regions. And initially, the Gulf Stream is also a warm current doing the same thing. Gulf Stream accelerates warm equatorial water northward. Okay, when it goes towards further north, it is known as North Atlantic Drift. The Canary current, look at this. The Canary current does what? It pulls the chilled water back. Whatever the chilled water is there, it will pull it back along the south. It will move southwards along the African coast. This is Africa. It will move it along the African coast. Boundary diagnostic matrix. We have already learned, right? Western boundary currents are what? Mostly they are the warm currents, right? Western boundary currents are mostly warm, fast, narrow, deep, and they move poleward, right? Move towards the poles. western boundary of continents. Okay, western boundary of the continents. First one is the in the North Atlantic Ocean we have the Gulf Stream current. North Pacific Ocean we have Kuroshio current along Japan, western boundary of Japan. In the South Atlantic we have the Brazil current, okay, moving polewards in the southern hemisphere, moving south. And East Australian current in the South Pacific, again moving towards the south along the western boundary of Australia. And Agulhas current in the Indian Ocean, basically moving again towards the southern pole. Eastern boundary currents are basically cold, slow, broad and shallow. They move towards the equator mostly. The Canary current in the North Atlantic moving towards the equator. California current in the North Pacific moving towards the equator. This is, can you see? Then there is the Benguela current in the South Atlantic, again moving towards the equator, northward. It is in the southern hemisphere moving towards the equator, Africa. And there is the Humboldt current, Peru current in the South Pacific moving towards the equator, northwards. West Australian current in the Indian Ocean, again moving towards the equator. Basin deep dive, the North Atlantic, we already studied this, right? Gulf Stream, North Atlantic drift, warm currents transporting warm water from equator to poles. East Greenland current, Labrador current transporting cold water from the poles moving towards the equator. The Arctic flush, the Labrador and the Greenland, East Greenland currents channel dense freezing waters southwards. The blue ones, they will channel the dense freezing water southward, creating volatile collision zones with the Gulf Stream. Can you see? They have a collision here, right? Then the heater, these are the red ones are the heater. The Gulf Stream transitions into the North Atlantic drift over time, okay, pushing tropical heat unusually far north. This specific thermodynamic transfer is what keeps Western Europe temperate. Otherwise, Western Europe in this region, Western Europe would be much colder if it was not for the presence of these warm currents. Okay, that presence of this Gulf Stream and North Atlantic drift causes Western Europe to have a temperate climate. The Pacific, what happens in the Pacific is that we have the Kuroshio current mirroring the kind of similar like the Gulf Stream. The warm Kuroshio current shoots northward along the western boundary of Japan, right? Past Japan, eastern boundary of Japan, past Japan before joining the vast North Pacific current. Joins here. The Oyashi collision. Here's the collision zone. Can you see? Cold and warm. Cold water from the Oyashi current descends to meet the Kuroshio, creating a highly productive marine boundary here. Collision causes a creation of marine boundary. We'll study about this. Here is a north and south equatorial current along the upper and lower parts of the equator. The massive upwelling happens here. The Humboldt Peru current along the western boundary of South America. The Humboldt Peru current is one of the longest after the west drift. Okay, it is one of the longest uninterrupted cold boundary currents on the earth, dragging frigid water directly from Antarctica, right? Directly from the Antarctic Ocean along the entire western coast of South America. It will travel along entire western coast of South America. The equatorial band. Along the equator, you would see that the currents are moving laterally, either right or left, but along a lateral path. Okay, not northward or southward. Okay, the westward, there are some westward push currents across all major oceans. The north and south equatorial currents march relentlessly east to west. They are moving from east to the west, driven continuously by trade winds, because trade winds move from east to west. So these winds, when they travel above the ocean water, they force the water to move in the same direction. The friction return. Trapped between these massive westward flows lies the equatorial, this is the equatorial counter current. Okay, this is a narrow distinct band of warm water, it's a warm current fighting its way back west to east across the doldrums. It tries to move in this direction but remains trapped here. Okay, tries to fight its way back west to east across the doldrums. You know, now the word doldrums basically is used to represent winds which are not blowing at all, no blowing of winds along the equator. So it kind of remains trapped here. The anomaly, reversing the engine. A standard flow looks like this, right? Gyre formations will be there. But monsoons disrupt this gyre formation. Unlike the permanent gyres of Atlantic and Pacific Ocean, in the Indian Ocean, we have monsoonal winds blowing, right? In the Indian Ocean, this is India, right? Indian Ocean dictated by seasonal landmass heating. So we have the monsoon drift. Maps only dash pathways represent seasonal currents. Driven by fierce monsoon winds, the surface flow completely reverses whatever direction we have in the standard flow of the gyres. That direction is completely reversed. If the direction was like this, it now goes like this. The direction was like this, it now goes in a different direction. Okay, overpowering the standard gyre, whatever were the standard gyre mechanics, those are completely overpowered by the monsoon drift. This is the unbroken current, the west wind drift. The unbroken loop, the west wind drift is the only ocean current that circles the globe without ever colliding with any continent. It does not collide with any continent, circles the entire continent of Antarctica. Because it spans all the longitudes, we know one longitude to another, all the longitudes, it acts as a major cold water source. This is a cold water source, right, from the Antarctic Ocean. Primary cold water source for the major southeastern boundary currents like Falkland, Benguela and West Australian currents get their water from the west wind drift only. This is how the map remains. Okay, continuous balance of heat is maintained. The net heat transfer, the intricate gyres, whatever the boundary currents and the drifts all serve a single macro purpose. What is the major purpose here? Preventing the equator from boiling, getting too hot, and preventing the poles from freezing solid. Okay, the continuous pump, warm surface currents, the red arteries, red ones, push the thermal energy towards the poles, from the equator towards both the poles, where the water cools, right? It sinks, it will cool down, it will sink and begin the long cold journey again, blue winds back to the water will sink and it will come back towards the tropics and towards the equator. Okay, so in this way the system is perfectly balanced. Climate divide, wherever warm currents flow, okay, we basically know that in the west coast, low middle latitudes, they are bordered by cool waters, cool currents are flowing here, results in leverage, so temperatures will be low, right? So relatively low average temperatures, narrow, there is temperature differences are very less, causes frequent fog but creates highly arid deserts are created, very dry deserts are created. Along the east coast in the low and middle latitudes, these are bordered by warm currents. We know that warm water will cause evaporation, right? Water vapor will be formed, it will collide somewhere and we will get precipitation or rainfall. Lying in the western margins of subtropical anticyclones, this results in distinctively warm and rainy climates. Okay, so east coast of the continents in the low and middle latitudes get a good warm and rainy climate, west coast get a cold and dry climate. In higher latitudes, what happens? The situation is reversed. In the higher latitudes, west coast receive warm waters, causing mild marine climates. Whenever we have studied that some cold currents collide with the warm currents, right? Whenever there is a collision, this kind of a situation happens. Okay, a good marine reserve is created here. The most biologically critical regions of the ocean occur where warm and cold currents physically collide, like this. Replenishment, the violent mixing replenishes vital oxygen levels. Whatever oxygen levels are depleted in some regions, it will replenish all those oxygen level. High oxygen levels will be maintained in this collision zones. Okay, bloom, favorable conditions trigger massive growth of plankton. You know, na? Beneath the ocean waters also there are some certain plants that grow which are known as planktons, right? Foundation for the marine food web, that is the primary food. Okay, that is where the food web starts for the marine ecosystem. So plankton growth is high in this region, oxygen gets replenished and fishes, huge fish population is found. Because of this biological density, these mixing zones contain the absolute best fishing grounds in the world. Wherever collision of cold and warm current happens, those become good fishing grounds. Okay, all over the world, wherever the collision zones are there you will get good fish counts. Okay, so that is all. If you would like to attend more of such classes, kindly join our classes through our website. I would love to guide you through more such topics in geography if given the chance. Thank you.